Okay, welcome to this week's hottest seminar. Today we have Norihiro Yamada, who will be speaking about game semantics of homotopy type theory. Go ahead.
Thank you. Thank you for organizing this seminar talks, and thank you for inviting me. And today, I'd like to talk about my recent work on game semantics of homotopy type theory. So let me begin with, Let me begin with some background. So just like axiomatic set theory is informally explained by sets, the conceptual foundation of Martin-Löf type theory is computations in an informal sense, also known as the BHK interpretation. So specifically, this interpretation interprets proofs and objects in constructive mathematics as computations. For instance, the successor function can be seen as a proof that there is no maximal element in a set of natural numbers. And this interpretation justifies MLTT as a foundation of constructive mathematics because it interprets everything as computations or constructions. On the other hand, homotopy type theory, which is an extension of MLTT, is motivated by the very different homotopical interpretation. And here, let me be specific in a point that by HoTT, I mean MLTT plus univalence axiom and higher inductive types, mainly to distinguish it from more recent cubical type theory. And this homotopical interpretation interprets formulas as topological spaces, proofs and objects as points, and higher proofs and objects as paths and homotopies. And in this way, HoTT uncovers new connections between type theory, higher category theory, and homotopy theory. And also it is a powerful foundation of mathematics. On the other hand, this topological view of HoTT is rather orthogonal to the traditional BHK interpretation of MLTT. And let me further post a bit arguable question, namely, are proofs given by working mathematicians really points in spaces? It's a bit arguable because it's only a philosophical question. But here, I mean, by proofs, some are like dialogical arguments or interactive processes between a prover mathematician and a disprover mathematician. And this looks like some computational process close to BHK interpretation rather than like a geometric object. So this intuition leads me to the following. So namely, I want to extend the BHK interpretation of MLTT to HoTT so that one can better understand HoTT as a foundation of constructive mathematics. And motivated in this way, my main result is the following. So there is a game semantics of HoTT, specifically MLTT with 1, 0 natural number, pi, sigma, and identity types, as well as univalent universes. And this game of semantics interprets types as games between player and opponent. I will define games formally later, but here you can think of games in the ordinary sense like chess and poker, and played between a player or a prover mathematician, an opponent or disprover mathematician, or oracle. And then terms as strategies, which are a certain kind of algorithms for player to play on games. And particularly, identity proofs as strategies that verify equality between strategies. And I find this is intuitively natural from the view of BHK interpretation because identity proofs should be some computation that verify equality between two computations. So if you regard strategies as a particular notion of computations, then you can think of this game semantics as a variant of the BHK interpretation. And also I have some technical corollaries. The first, actually this game semantics validates strict univalence in a sense that the judgmental equality between identity on universe and type equivalence holds. So as an immediate corollary, it showed the consistency of HoTT plus this strict univalence. And also, this game semantics showed independence of Markov's principle from this extended HoTT. Right, but at this point, one might wonder why I choose game semantics, because there are many other computational models, most notably realizability models. And a possible answer would be the following advantages of game semantics. So first, game semantics has been very effective for the study of type theory, something like independence of Markov's principle. And on the other hand, for instance, high-length effective topos cannot show independence because it validates Markov's principle. And secondly, game semantics has an elegant interpretation of computational effects and linear logic. So one can hope for from game semantics HoTT to get some nice combination of HoTT with effects and or linear typing. And another application of game semantics is in program verification and model checking, known as algorithmic game semantics. And finally, by its intentionality, game semantics is actually rich in its higher structures. And that suits the interpretation of higher structure of HoTT. And the first 3 points are nothing new. It's well known in the literature. But I think the last point is, in some sense, new. So let me explain and the last point in the next few slides by introducing what games and strategies are. So let me remark here that the games and strategies I introduced here is actually much simplified than what I'm actually using. But I think such a simplification will be appropriate for this talk because yeah, the formality is a bit too technical. So I just please bear in mind that the actual games and strategies are mathematically much more sophisticated than what is present here. Okay, so game is a rooted, directed acyclic graph or DAG, whose vertices are called moves. And it is assigned a parity OP, representing opponent or player, and every path from a root called position as a parity OP and OP. And the intuition here is that the game in an ordinary sense, like chess and poker, can be represented by a DAG in which a root represents the first move of the game. And then along a path from a root, a play of the game proceeds. And in a standard game, it is always opponent who makes the first move. And that's why root has a parity O, meaning that it is a move by opponent. And then a path has a parity OP, OP, meaning that player and opponent alternately perform moves. So let me give some very simple example. This is a game for natural numbers. And it consists of the root, which I write by Q, meaning that it's a question by opponent. And then player moves corresponding to natural numbers. So play in this game proceeds as follows. So first, opponent asks a question, like saying, what is the number? And then player can answer by any natural number, 0, 1, 2, or whatever. And that's it. It's a very simple game. And next, let me describe a game for function type from natural number to natural number. To construct such a game, we first need 2 copies of natural number game. And here I'm introducing some abbreviation. So here, n and m are variables ranging over all natural numbers. So this is just an abbreviation of this natural number game. And this shape also abbreviation of natural number game. And we have two copies on domain and codomain. And next, we flip this parity. Sorry, we switch the parity on the domain game. So now Q becomes player's move and N becomes opponent's move. And finally, we add an additional edge from every opponent move on the codomain to every player move in the domain. So, so this one in this case. And similarly, from every opponent game in the domain to every player move in the codomain, we also need to add an edge. And this is a game for function type from n to n. So in this game, again, this is the root. So opponent ask a question saying, what's the output? What's the number? And then player now has two choices. And if player chooses to go to domain, then a player asks a question here. Okay, but wait, what's the input? Then next opponent has to provide some input, say n. And then finally, player has to provide some value m. And if player chooses to m to be, say, n+1, then this computation corresponds to successor function. And that's why this represents a game for function type. And instead, player can also choose to play after the initial question immediately to m. In this case, this corresponds to a constant function valued at m. Okay, next, let me introduce the notion of strategy. So a strategy sigma on a game written by sigma colon z is a map from odd length positions in z to a player move in z, such that the concatenation is again a position in z. And because every path from a root in a game has parity OP, OP, odd length positions are exactly when player has to make the next move. So a map of this kind is really a strategy for player on how to play in Z. And I can describe the successor computation as strategy of this form. So this maps from Q to Q, so from Q to Q, and given QQN, so QQN, outputs n+1.
Can I ask a question at this point?
Yeah, sure.
So you mentioned that the constant function could be encoded by the player just immediately choosing an output m.
Mm-hmm.
But couldn't it also be encoded by the player saying, tell me what the input is, and then ignore it and always choose the output m?
Exactly, and actually you read my next slide. I will explain this point in the next slides.
Okay, perfect, thanks.
Thank you. Okay, so
Sorry, supplementary question probably on the next slide as well. I mean, what you described so far could equally be said to be describing relations between numbers and numbers rather than, you know, single valued functions. So presumably there's going to be some kind of restriction, is there?
Sorry,
some kind of consistency, you know, so that you don't answer different things for the same argument, as it were.
Right. What do you mean by, sorry, same kind of argument?
Well, when I play the game, right, if I'm describing a function, I'd expect to get consistent answers. I don't find the function has a value 3 and the value 4 at argument 0, as it were.
Right. Yeah. I
mean, his strategy is a function. Like he called it a map. So doesn't that mean it will be consistent in the sense you're asking about?
Sorry, I'm confused by what does it mean by consistency?
He means single valued.
Okay. Yeah. There are two ways of describing a constant function, single value function.
No. He means single valued in that for any given input, there's only one output.
Yeah.
But I don't understand the question because a strategy is a function, so it should have that property.
Yeah, I see what you mean. Why don't you just carry on?
Yeah. Yes. Sorry. Yeah. Let me go. And I hope next slide will answer your question. So I want to describe intentionality of games by some simple example. So there are actually two strategies on function game, both representing constant zero function. The first one is of this form. So for the initial question, player asks back what's the input, and opponent gives some input n. But whatever n is, player simply always output 0. So this is one way of representing a constant function. And another is just I described in a previous slide. It immediately outputs 0 without asking any input in the domain. So both extensionally the same function, namely constant 0, but they are intentionally or from the view of strategy different. So this illustrates the point that the category of game is not well pointed. So this is a typical kind of intentional nature of game semantics. And let me further give some other examples and games for identity types. And first one is identity game between two numerals of type n. This is a certain kind of substructural game of this function game. So in this game, you can play only of this form. So namely, for the initial question, player has to ask back the input. And then whatever input n is, player can only copy and paste and other output. And this strategy is valid if and only if n and m are equal. And it's not valid if n and m are not equal. So in some sense, this higher structure of natural number game is trivial. It's something like, empty set or singleton set. On the other hand, I define identity on function type between phi and psi by the following formula. So this is coming from basically function extensionality. And I'm cheating here, of course, because I haven't defined anything like pi on games yet. I will define it later, but I just want to informally describe here. And the intuition is pi is a dependent generalization on function. So recalling the construction implication between game. So we have one copy of n on the domain and a copy of this one on the codomain. So as a result, we get this game. So we have natural number game n. Now I abbreviate as QM. And we have on the codomain a copy of this game. And then again, we flip the OP parity on the domain. And finally, for every O move on the domain and to every P move on the codomain, we add arrow. So in this case, this arrow and this arrow. And similarly, we have to add from O moves here to P moves here, an arrow. So in this case, this one and this one. And as a result, we get this game mean to be interpretation of this identity. So a typical play in this game proceeds as follows. So given the first question by opponent, player asks a question And then opponent gives some n, and then player finally outputs n. So play exclusively occurs on the codomain. Or a player can choose after initial question to ask a domain question Q, and opponent gives some input M. And then player go back to codomain and play in this way. And in this case, of course, given M, this N should be phi M, and this should be psi M. So there is a strategy if and only if phi M and psi M coincides. And just a point here is that this game for identity on N has trivial higher structure, namely only one trivial strategy. But even from this trivial higher structure, the higher structure of implication is no longer trivial because we have at least two different strategies. One is this one, and another is this one. So this is a glimpse of the rich higher structure of game semantics coming from its intentionality. And that suits as an interpretation of rich higher structure of homotopy type theory. That's illustration of my last point, why I choose game semantics as a computational interpretation of homotopy type theory. Okay, so let me finish this introduction by mentioning briefly some related work. First, a pioneering constructive model of HoTT is cubical set model initiated by Bezen, Koch, and Huber, and later developed by many others. And it's homotopical in nature since it can be seen as a constructive variant of Voevodsky's simple sets model. And its constructivity refers to the constructivity of the meta theory. Later, this constructive meta theory internalized by assemblies and type theory, known as cubical assemblies and higher dimensional meaning explanation. And this line of work on cubical type theory. And so the unit interval dimensional variables and path types play crucial roles. On the other hand, my approach is a BHK-interpretation of HoTT. So it's rather computational than topological, and it's on book HoTT, not on cubical type theory. And another point is that it is based on infinity categories based on globular sets rather than cubical one. So there are some notable differences between the existing approach and my approach. Okay, so let's get some overview of my approach next. Okay, so throughout this work, infinity groupoids refer to strict infinity categories a la globular sets whose morphisms are weakly invertible in a sense of type equivalence. I will make explicit what I mean by weakly invertible in a sense of type equivalence later, but just please bear in mind that the underlying categorical structure is strict, while groupoid structure is weak. And then define game semantic infinity groupoids to be infinity groupoids in this sense, internalized in the category Z of games. But here strictly, it is internalized in the subcategory G check of Z, which forms a topos, because G itself is not finitely complete. So we need to use a subcategory which is finitely complete because we need at least pullback to internalize composition. But on the other hand, we need a generality of Z later to internalize infinity functors and transformations. So actually we need both G and G check, but this is just a minor remark. It's not that important in the rest of the talk. Okay, and before unpacking this definition, let me make some a few remarks. First, my approach is based on Mihail Warren's strict group point model, actually strict infinity group point model. But of course, we need to modify it because our inverses are only weak. And we then internalize this modified infinity group point model in the category Z. And of course, the challenge is how to recover Warren's method with weak inverses. This is a bit technical, but idea is basically the same. So I wouldn't go into detail in this talk. And finally, my approach can be generalized to finitely complete categories families, say M, with a natural number object, such that each semantic type A in a context gamma is a map from the set of this global element to the set of objects. So in the rest of the talk, I will describe my method in this categorical level without going into much detail of game semantics. Okay, so let me unpack this informal definition. So the idea is basically internalize the notion of strict infinity categories in the ambient category Z. So that means explicitly a game semantic infinity category Z consists of a globular set, but now this is a diagram in G-check. So each G0, G1, and G2 are games and sources and targets strategies that satisfy globular equations. And then we have a morphism in G-check that serves as a composition, where this is a pullback of this form. So this pullback, the first projection composed by iterated source and second component with iterated target coincide. So this is just a composability of two N cells with respect to P cells. So in this way, this morphism represents a composition operation internally in G-check. And finally, we have another morphism in G-check, which is identity. So given N cell, it outputs identity on that given N cell. And of course, these structures are required to satisfy the axiom of strict infinity categories in terms of appropriate commutative diagrams in G-check, such as interchange law, associativity, unit law, and so on. And moreover, a game semantic infinity category Z is a game semantic infinity groupoid if it is equipped with the following four morphisms in G-check with the expected sources and targets, and also their factorial on the nodes. And I will explain shortly what expected means here. But intuition here is that this morphism is a inversing operation. And this is a witness of retraction. And this is a witness of section. And this is some triangle equality-like coherence between retraction and section. So I think one way to describe this is as follows. So given an N cell, which is a global element of this form, one gets by composition with this morphism inverse of F. So this domain and codomain of this form. So namely, domain and codomain of F is flipped. And then by composing with this morphism called retraction witness, we get kind of inverse of unit in adjunction. So domain is this one, and this is codomain is the identity of the source of F. Yeah, so this witness is, retraction of F inverse as a retraction. And dually, by composing with a section witness morphism, we get kind of co-unit or witness of section. And finally, by composing with triangle witness, we get witness for this coherence between section retraction. And this is the last component of the half adjoint equivalence or type equivalence in homotopy type theory. So basically, these four structures correspond to type equivalence. And this is the main idea how we model univalent universes, as we shall see later in this talk. All right, so this is an explicit definition of what I mean by game-semantic infinity groupoid. So let me next describe what I mean by game-semantic infinity functors. Okay, so just as a notation, let me define ordinary infinity groupoid out of game-semantic infinity groupoid Z, which I write G double bar by this formula. And the remaining structure like composition identity can be given by the usual Yoneda style argument. And then roughly, game-semantic infinity functors between game-semantic infinity groupoids G and H strategy, say phi, which is of this form. And this is a set of semantic term in a categories families of game Z. And the domain is a natural number object, which is a game of natural number I described in a previous slide. And this is a semantic type over N defined by this formula. So every numeral, which is a global element of this natural number object, is given by this one. So namely, exponential object from game Gn to Hn, such that phi star, which is a family of a composition of phi and numeral n, which is a strategy from Gn to Hn, because phi is of this form. So the idea here is each component of this family is served as an internalization of each component of infinity functor. So indeed, this should form infinity functors between underlying ordinary infinity groupoids. Yet this is internalized in Z. And finally, this should preserve the data of inverses. So in other words, phi is a strategy such that this family should satisfy the following functoriality. Namely, this preserves sources, targets, composition, and identities. And the preservation data of inverses can be formulated in an analogous way. Yeah, so the idea is, so a family of components of infinity functors unified into a single strategy of this form. That's the basic idea. And here's a little lemma. The category, which I write this, of game-semantic infinity groupoids as objects and game-semantic infinity functors as morphisms can be extended to infinity category, in which higher cells are certain notion of internalized natural transformations, which I define in the next slides. But before doing that, let me just extend this operation to a functor from this category to the category of ordinary infinity groupoids by defining its arrow map as follows. So basically, the arrow map of this functor sends every game-semantic infinity functor phi to the following ordinary infinity functor, which I write a phi double bar, namely by the operation post-composition. And then with this mind, roughly, the notion of game-semantic transformations, which are higher cells in this infinity category, can be defined as follows. So define a game-semantic natural transformation or a transformation between game-semantic infinity functors phi and psi to be transformations between these underlying infinity categories, yet internalized in Z. And similarly, for higher transformations. So this is just idea. So more explicitly, a game-semantic one transformation from game-semantic infinity functors phi and psi is just a morphism in Z, or just strategy. Alpha from game G0 to H1. This is just a straightforward internalization of natural transformation, because natural transformation is parameterized by objects, and each component is a morphism in the codomain. So this is just a internalization of ordinary notion of natural transformation. And then our source is phi star 0, and target is psi star 0, because it's between phi and psi, and satisfied ordinary naturality condition. And it is similar for higher natural transformation. You can just replace H1 with H2, then you get a notion of game-semantic 2 transformation, and so on. And let me then extend the functor further to an infinity functor by defining Daruba alpha to be the following transformation. So namely, each component with respect to gamma is given by post-composition. Right, so this completes the structure of infinity category, this one. Okay, now we can get some overview of the interpretation. This closely follows Mihail Varen's approach. So we interpret every context as a game-semantic infinity groupoid. And we interpret every type as infinity functor between this infinity groupoid to this infinity groupoid. But here I'm cheating, because I have just shown that this is only infinity category. But later, we extend further this one to an infinity groupoid. So this definition actually makes sense. And we interpret term A as a section of the first projection. And here, gamma dot A is a Grothendieck construction. And we interpret identity proofs of this form as a game-semantic 1 transformation between game-semantic infinity functors A1 and A2. And then naturally, we interpret even higher identity proofs as a 2 transformation between 1 transformation. A game-semantic 2 transformation between game-semantic 1 transformation. There are particular kind of strategies, and so on. And this is just a straightforward internalization of Varen's approach. And we can interpret 1, 0 natural number types by discrete game-semantic infinity groupoids. They are just usual games equipped with trivial higher structures. And identity type basically by this formula. So identity of A is parameterized by gamma on a large gamma, and 2 strategies alpha 1 and alpha 2 on A gamma. And this is given by this structure. This is the substructure of this object. So namely, a higher structure of this substructure is always bounded by alpha and alpha 2. And this again just follows Varen's approach. So I wouldn't talk about it in the rest of the talk. And instead, I focus on some novel points, which are in my interpretation of pi type and univalent universes. And let me first sketch my interpretation of pi type. And the idea is basically the operation carrying in game semantics is trivial. So we just apply the interpretation of terms here as an interpretation of pi type. So specifically, okay, let me omit the semantic bracket here for brevity in the rest of the talk. And I interpret pi type from gamma to A, which is a certain kind of game semantic infinity groupoid as follows. So those cells are sections of this form. So basically, this is just interpretation of term from gamma to A. And higher cells, say from sigma to tau, are game-semantic transformations. So these two are basically following the interpretation of terms. And then I define composition of N cells with respect to P cells as the internalization of the following algorithm in Z. So namely, given two N cells, so they are sigma and tau, just a game-semantic N transformation. So they are strategies from gamma 0 to gamma dot AN. Then this algorithm first take the product here, and then precompose diagonal, and then post-compose composition on the codomain. And as a result, we get N cell or N transformation from gamma 0 to gamma dot AN. And similarly, or even more, in a simpler way, the identity can be given by the following algorithm internalized in Z. So namely, given sigma, it just post-compose identity on gamma dot A. And similarly for data of inverses. So you can just replace IN here with these operations on gamma dot A. And this categorical recipe actually really specialized to game semantics really makes sense as a structure of pi as follows. So here, just bear in mind that the interpretation of higher cells on pi are game semantic transformations, so strategies of this form. Okay, so this notion of identity proof really makes sense as identity proofs in pi type as follows. So let me come back to the example that I define identity between phi and psi of function type as a following game. So a domain is game N, and codomain is an identity game between natural number. And here I introduce a notation. So function of phi is just a set of input-output pairs of phi, and similarly for psi. And so in this game, so actually there's a strategy if and only if phi of n and psi of n coincide. In other words, there is a identity proof if and only if phi and psi are extensionally equal. So by this definition, it validates strict function extensionality. But this interpretation is non-trivial because, as I said before, there are at least two different strategies. So one is here, assuming that phi n and psi n coincide, and another is like this one. So it is a non-trivial interpretation of identity proofs that validates strict functional extensionality. And please note that this is a game semantic transformation because a domain is n and codomain is identity proof on a function type. So identity proof on n. So it's like n0 and n1. And here, I want to make the point of the beauty of game semantics. So the domain n is in some sense infinite because there are infinitely many natural numbers. So if there's only player, then player has to pick input n and compare phi n and psi n. But this verification never completes because there are infinitely many natural numbers. But in game semantics, computation is always with oracle or opponent. And it is opponent who gives us the input n. And if phi and psi are different, only one particular input, say n, then opponent can immediately detect such n and provide n as an input. So that there is no identity proof in that case. So in other words, if infinitely verification of equality between phi and psi reduced to finite, more specifically just one round verification of this form. So this makes sense as a constructive or even finitely verification of equality between phi and psi. I find this quite nice. And let me finally add another interesting point. So namely, higher cells in pi are only weakly invertible, even if a higher structure of n, natural number game itself is trivial and trivially strictly invertible. Because identities in pi or like reflexivity in pi strategies that never visit the domain. So diagrammatically, it just stays in the codomain and play like this. On the other hand, composition in pi cannot undo such visit. Sorry, sorry, maybe I will go back to the previous slide. So here is a composition of higher structure in higher morphism in pi. And suppose that sigma is a strategy such that at some point it visits domain and computes in the domain. But by this definition of composition, whatever tau is, this composition will also visit at some point the domain, gamma 0. However, reflexivity or identity, trivial identity proof on pi is a strategy that always computes on codomain only. So this composition cannot be strictly equal to reflexivity. In other words, there cannot be any tau that is a strict inverse of sigma. And that's why we only have weak inverses in pi. And this suits our choice that underlying infinity category is strict, while groupoid structure is weak. Okay, let me quickly finish, finally sketch by sketching my interpretation of univalent universes. So there are two steps. First is that we need to extend the infinity category, this, to an infinity groupoid, as I promised, in which higher cells correspond to type equivalence. And then we extract a substructure of this structure, say U, which consists of game-semantic infinity groupoids freely generated by type construction. And so that we can encode game-semantic groupoids by strategies on this game U0. And then the higher structure just trivially restricts the rest of the structure of this one. Okay, let me first describe the first point. So the following construction extends the infinity category of game-semantic infinity groupoids to an infinity groupoid. First, those cells remain to be the same, so they are game-semantic infinity groupoids. And here is the main idea. One cell from G to H are quintuple such that the first element phi is a game-semantic infinity functor from G to H. And a second component psi is meant to be the inverse of phi. So from H to Z. And third component sigma is meant to be retraction witness or unit, so of this form. And tau is meant to be a co-unit, so of this form. And finally, mu is meant to be the coherence between sigma and tau. So this quintuple exactly coincides the type equivalence or half adjoint equivalence in HoTT. And that's the main idea how I interpret univalence. And the remaining interpretation is more or less the same. So higher cell between these quintuples, just quintuple between phi and phi prime. So alpha is between phi and phi prime, beta between phi prime and phi, and so on. So I wouldn't go into much detail here. And the challenge is then in turn, how to define inverses and compositions and so on these quintuples. And the inverse of each n cell, which is a quintuple, alpha, beta, eta, epsilon, delta, is given by this formula. So basically, we switch between alpha and beta here, and switch between eta and epsilon here. And then the last element is a bit technical to present here, but we can construct such an element of the appropriate form. So it's a coherence between epsilon and eta. And identity operation is just trivial. Basically, we just apply identity operation component-wise. And here, this operation is not circular because identity operation on the right-hand side are coming from the ambient infinity category. And finally, retraction can be defined by extracting the third element and then apply the operation on ambient category, infinity category, and similarly for section witness and triangle witness. And lastly, composition can be defined by case distinction, but yeah, let me just skip this point. The point is just we can define by such formula. And this completes the first point. And let me just finish the second point. So idea is to define game U0 in such a way that strategies on U0 can encode type construction in the following way. So in U0, a game always starts with opponent question Q, and then followed by some arbitrary fixed Gödel numbering of game. So if I want to encode natural number game N, and then this strategy on U0 proceeds as follows. Given opponent's question Q, player answers the Gödel numbering of N, saying that my game is N, and that's all. And in the case of sigma, again, opponents ask a question first in this game U0. What's the game? And player answers by the Gödel numbering of sigma, saying that it's a sigma. And the opponent can proceed to ask the first component A or second component B. And if A is, say, N, then a play here just looks like play here. And similarly for the construction pi. And finally, we can encode identity game as a strategy on U0 as follows. So again, it starts with opponent's question, what's a game? And then player answer by the getter numbering of identity. It is identity game. And then finally, opponent can ask the underlying game A, or two strategies being compared. And here, player can just proceed as in Sigma. And here's a little point that it is in general impossible to encode strategies alpha and alpha 2. But then we can just play alpha 1 and alpha 2 themselves, so that we can circumvent the issue of encoding alpha and alpha 2. And in this way, we can also encode identity game construction by a strategy on U0. That's roughly the idea of how we construct the interpretation of universe. But the main point here is that higher cells are quintuple. Sorry, higher cell in universe are quintuple. And so this just coincide type equivalence so that we can interpret strict univalence. That's the main idea. And here, let me stop my talk. Thank you for your attention.
Thank you very much. So we'll do our usual visual applause. And we open the floor to questions. If you have a question, just go ahead and unmute your microphone.
I'll ask a question. It's very interesting that you're using strict infinity groupoids. I guess because we know that classically strict infinity groupoids don't model homotopy types, don't model all homotopy types. So I guess I'm just curious how your construction avoids those problems, if that makes any sense. Like for instance, at least under a naive interpretation, the braiding, the higher structure like pi3 of S2 or something would be trivial in a strict groupoid. So how do you avoid that sort of problem in interpreting HoTT where you could prove that it isn't trivial?
Right. I haven't checked that point yet. I was focusing on to get a constructive model. But one possibility would be actually the structure of a strict infinity category, I think can be weakened by incorporating my work jointly with Samson Abramsky called dynamic game semantics, which makes strict structure of category to weaken. So, in that work, two category becomes bi-category, and similarly, I think there is actually a weak structure underlying this strict work. It can be a solution, but in my case, as you say, this model itself trivialize some of the higher structure. I haven't checked that point yet. But at least, as I said, the inverse structure, group structure is weak.
So Mike, does that really answer your question though? I mean, you can
my answer is I haven't checked that point yet.
Well, yeah, I'm just worried because, as I said, like if you had an interpretation of HoTT, then you should be able to encode the proof that pi3 of S2 is non-trivial. And so if that's true, then somehow the meaning of pi3 of S2 must not be the naive meaning in a strict infinity groupoid, because in that case it would be trivial.
Mm-hmm. Thank you. Yeah. I would double check that point.
Any other questions?
Yeah, hi. Hey, so I was wondering if it's possible to use game semantics to first construct a model of extensional type theory and then, for example, carry out Michael Warren's construction internally in the model of extensional type theory. I was wondering if this would be I mean, if it works, if it'd be the same as your construction, or what would be different otherwise?
So as I said, in short, I think it's not possible, at least currently, because as I said, the higher structure of pi is automatically holds the invertibility only weak. So even if we start with strict invertibility on atomic types like a natural number, we automatically get non-strict, so weak invertibility along the construction of pi. So my construction cannot remain in the world of strict infinity groupoid.
So is that like all of the construction, or just maybe part of it could be, but then pi types, for example, might maybe not?
So for now, I observe it's on pi, but also I need to weaken invertibility so that I validate univalence. But as you say, if your aim is to model extensional type theory, it's not necessary. But as I said, due to pi, I think it's not possible.
Okay, thanks.
Thank you.
Okay, next question. Maybe I can follow up with the question I asked about the constant functions.
Mm-hmm.
So I couldn't quite tell from what you said after that. If I take two different constant functions, one of them that doesn't go to the domain and one that does go to the domain but ignores it, are they propositionally equal? Are they equal in the identity type that you create?
So they are proportionally equal because I define equality on pi just by the definition of function extensionality.
Right.
Yeah.
Good. Okay.
So I have a question. I'm getting kind of two things here, which I'm finding hard to kind of distinguish what's. They're probably both key, right? So one thing is kind of to do with what Mike asks. You know, if you start with a notion of some notion of infinity groupoid, weak or strict or whatever, there are a number of axes along which you can ask for strictness. You know, is composition strict? Is the unitary law strict? R inverse is strict? And you're sort of telling us that you can have good strict composition and good strict unitary, but you'll make the identities weak and good things happen. So that's one of the things that you're doing. And the other, of course, is that you're using games. And I suppose the game aspect must be essential for this to work, but I'm not seeing exactly in what way it is essential. So I suppose the question I'm asking is, do you think it would be possible to axiomatize in category theory what the properties of your games are that you need? You know, I'm thinking in terms of people have looked at various kinds of monoidal structure that categories of games have. Would it be possible to isolate what you actually need?
Sure.
Yeah.
So on that point, I briefly mentioned. So in short, it's yes. I believe yes. It can be axiomatized in a categorical level, and so And I believe that, so the last point, so generalized to finitely complete categories families. So for this model construction, I believe that you can also employ, say, a realizability approach. And you can similarly internalize univalence construction.
That would be very interesting, I think. I mean, games are great, but whenever I get exposed to them, at some point I always lose the will to live, because usually it's to do with the fact that you have to define the notion of strategy in some really careful, complicated way, you know, with views and all that crap, which of course you haven't mentioned, but I suppose, as you said at the beginning of your talk, you are simplifying a bit, right? I mean, the technical details. Is the notion of strategy as simple as you said, or is it actually more complicated?
Strategy is basically the same, but games are a bit more complicated. Okay. So yeah.
I mean, I would be strongly in favor of seeing the kind of general axiomatic thing in which maybe realizability was also an example. I mean, that would be great.
I see. Thank you. And let me just add that, some point or advantage of specializing in game semantics, as I said before, by such intentionality, it can be like useful for meta-theoretic study of type theory, like independence of Markov's principle and so on.
Yeah,
so,
yeah.
I
agree. Yeah.
Thank you for the question.
Okay, more questions? Okay, if not, then let's all thank Norihiro again. All right, and our next talk is in 2 weeks at the usual time, and we'll have Carlo and Julie speaking at that time with an interesting title, TBA. See you then.